Welcome everyone to the second part of the session of Weather and Climate Extremes General. So there are 4 blocks in this session. The first one, which was on wildfires, was earlier today. So if you're interested, please go and check out the recording or the presentations from the others. So this is the second block, which is focused on the heat waves, in particular on the 2021 heat wave. Bienvenue à tous à le deuxième bloc de la session extrême météorologique et climatique générale. Dans cette bloc, il s'agit dans les vagues de chaleur et aussi principalement il s'agit des vagues de chaleur de 2021. We have 6 talks. I will be starting the first part. So the first part of the session, Madam Kirchmeier-Young will be chairing it. So I'll stop sharing the list of participants and we'll start with the presentation itself.
Yep, while Lisa brings up her slide, I will just introduce her. I'm going to chair the first 2 sessions the first 2 talks since the organizers of this session are also presenting today. So the first presentation is by Elizaveta Malinina. She is an extreme event attribution scientist at Environment and Climate Change Canada, and I will let her take over. She's ready. Just a reminder that there is a chat box and a Q&A on the event platform. Please put any questions for the speaker in there, and I will read them at the end of her talk.
Hey, thank you, Megan. So the topic of my presentation is called the 2021 heat wave was less rare in Western Canada than previously thought. And this is based on the paper we published earlier this year. So when we are talking about the 2021 heat wave, we usually good to remember that it was very, very hot in British Columbia. So on the top panel of the slide, you can see the alerts from Twitter, from Environment and Climate Change Canada, from June 27, 28, and 29. And you can see that day after day, the national maximum temperature record has been broken. And it was broken in Lytton, in the small town on the mainland BC. So I don't live in Lytton, I live in Victoria. And I don't have very good photos from the 2021 heat wave. However, I quite like the feed which I had on my phone about this. So apparently on the 27th of June, 2021, I went to the beach. And it's actually an important part because the idea is that in Victoria and Vancouver, a lot of buildings are not air conditioned. So, and this was still in the middle of COVID. So going to a cooling centers, some people considered dangerous. And so essentially going to the beach was the only way to cool yourself down because you can go in deep into the cold ocean. But then after the 27th of June, my brain escalated, and from the 28th of June, I have the print screen from Twitter. And apparently on the 1st of July, I watched The Day After Tomorrow. So you can see what was going on in people's heads for the people who lived through the 2021 heat wave. But it wasn't hot only in BC, actually. So on this slide, you can see the temperature distribution maps over the western of the Pacific Northwest. And you can see that it was warm not only in the lower mainland where Lytton is located and where which actually made a lot of news headlines, but it also was warm, like it was also hot in the whole BC, even at the north, as well. It was the temperature records were broken in Alberta, Saskatchewan, Washington, and Oregon. So right after the event happened, because it was so unusual, 50 degrees Celsius, almost 50 degrees Celsius in Canada, in a northern country, a lot of studies started to come out about the event. And so all of these studies were mostly based on the data set, ERA 5, which is back in the day was started in the 1950s. And so all of these studies, they were calculating the return period of this event, and everyone got, for the BC or similar region, got the return periods of around 1,000 years. I also did the same. I took the data from 1950s to onwards. So here you can see the time series for the maximum annual maximum temperature in BC, and you can see how much 2021 is outstanding in comparison to all the previous years. However, it took me quite long to write this whole thing down, and while I was waiting, and I was preparing the paper, Copernicus published the data for the for the 1940s. I decided it most likely won't change my results, but why? It wouldn't hurt to look at the 40s as well. And how big was my surprise when I updated this time series for the 1940s, and I have seen this peak in 1941. So my first thought, which I've seen this, something is wrong. Artifact must be wrong, right? To verify that this 1941 peak was not an artifact, we've looked at HADEX3 data. So HADEX3 is the data set, grid data set, which provides the data on these climate extremes. And the first thing which you can see when you look at this plot, this enormous amount of pink. So this essentially indicates the grid cells in which 1941 was the year with the annual maximum temperature. Essentially, it shows that 1941 was a record year in most of British Columbia, Alberta, and Saskatchewan. So that gives you a clue that, yeah, maybe this peak was not wrong. We also looked at the data from weather stations. So here you can see the time series for 3 stations in BC on the top panel, 3 stations in Alberta in the middle panel, and in the bottom you can see 3 weather stations in Saskatchewan. So the blue dot indicates the 1941 event, and the yellow dot indicates a 2021 event. And you can see that indeed the 1941 was so outstanding. And in some stations, it was actually even larger than 2021 event, for example, in Vegreville and in Nipawin. So this all tells us that 1941 event in Era 5 was not an artifact. It was not a fluke. And indeed, we also can find the mentioning of 1941 heat wave and how bad it was in Victoria Daily Times. And you know that this was indeed something very special because 1941 was the year of the Second World War. So people had other thoughts in their minds. So when you calculate the return periods using the full time series since 1940s, you get much lower return period than 1,000 years. So for BC, the best estimate of the return period is 236. So almost 4 times smaller than previously reported. Interestingly enough, the 2021 is more extreme in Alberta rather than in BC, based on our estimates. Another interesting fact is that actually 1941 event was rarer for 1941 climate than 2021 event for the 2021 climate. The idea is that when we are trying to estimate return periods, we usually fit the distribution using global mean surface air temperature as a covariate. So what essentially these whole results tell us that all these return period estimates which we are doing, they're so sensitive to the region of choice, as well as they are very sensitive to the time series which we are taking into account. So our goal with the study was actually to calculate, to attribute this event to climate change. And so we also considered not only Era 5 data, but we also considered CMIP 6. results from CMOS models. And I know the tables are boring, but the most important parts here are these blue and red highlighted parts. And what essentially they tell us that there is a difference between in the return periods from era 5 and CMIP 6. And for BC, the CMIP 6, the return periods in CMIP 6 models each much higher than based on our error estimates. And for Saskatchewan, it's vice versa. The return period is much lower than what we've seen in era 5. So the question is, what's the reason behind that? So on this slide, you can see the standard deviations for 1940 from 1940 to 2022 from in the different CMIP 6 models, which are depicted with these dots. And on the left-hand side, you can see the results for BC. On the right-hand side, you can see the results for Saskatchewan. And so on the left-hand side, what you can see that all the dots are located to the left from the red bar. Red bar indicates the standard deviation from error 5. Versus on the right-hand side, it's exactly the opposite. Most of the dots are located to the right from the red bar. Essentially, it's saying that there are differences in between in the variability of in models and observations. So that's the reason why we see these different return periods. So, but what about the attribution itself? So here you can see the results for Alberta. So what we are doing in attribution is that usually we are looking at the event and the probability of that event in the current climate, which is in this case depicted as orange line on the left-hand side, and the red bar indicates the event itself. And you can see that these distributions, they move. So the green is to the left from the orange, and orange is on the left from the blue, which indicates the future climate. So essentially what that means, that the probability of the 2021-like event is changing with the time. And so there was a significant probability increase in the current climate in comparison to the pre-industrial. And so we see that it's the event 2021-like event is 25 times more likely in comparison to the pre-industrial, and will be 16 times more likely in the future climate in comparison to the current one. So with this, I'm coming to the end of my talk. So on the right-hand side, you can see the QR code with the paper. If you're interested, feel free to check it out. There is much more information which was covered in this presentation. But the things which I want you to remember from this is that the 2021 heat wave was much less rare in BC than previously thought. That the length of the time series to the return period estimates, as well as the region of choice, do matter when we are given particularly this like very long return period estimates. That there are differences in variability of maximum temperature in the models and era 5. So for some regions, we see the differences in the return periods in between those two data sets. And the last point is that the human-induced climate change made the 2021 heat wave much more likely in comparison to the pre-industrial climate. And with that, thank you so much for listening.
Great. Thank you very much, Lisa, for a great presentation. We have time for a couple questions. A reminder that you can put them in the chat or the Q&A box on the webpage. While I wait a moment to see if any pop up, maybe I'll take the benefit of being chair and ask you one myself. Have you noted that more recently the 1940s from era 5 was released. Have you noticed a change in the literature, more people using back to 1940, or is it still predominantly starting in 1950?
So as you know, like it takes very long time to publish a paper. So I've definitely seen a few studies nowadays, like published more recently the last half a year, but 1940s were used. But at the same time, a lot of people are still not aware that error 5 is now available from 1940 onwards, and some people still don't trust the data that well. So yeah.
Great, thank you. I don't see any other questions online. So I think we could go ahead and move on to our next speaker. Thank you, Lisa. Our next speaker is Nathan Gillett, who's a research scientist at Environment and Climate Change Canada. Go ahead, Nathan.
Thank you. Hopefully you can see my screen.
Yes.
Great. Okay, so thanks, Megan. So I'm going to be talking about a rapid event attribution system for heat waves in Canada. And this follows on very nicely from Lisa's talk. So the system I'm going to be describing is based on work by Lisa, and also with contributions from others in the team, including Megan and Yongxiao Liang and Konstantinos Menelou and other colleagues. After an extreme event, media and the public typically want to know whether the event in question was affected by human-induced climate change. But not just the public, policymakers are also interested. For example, if we think of the 2021 floods in BC, a lot of infrastructure was destroyed and damaged. And if you're a policymaker, someone responding to that, it's useful to know whether that kind of event has been made more likely by climate change and whether it's something that's expected to become more frequent in the future. But event attribution studies, as Lisa just said, they typically take at least several months, if not years, to carry out. So the motivation here is to try and be able to provide results on a faster timeline when they're more relevant to the public, to decision makers. As it says in the title, we're developing a rapid event attribution system to provide this kind of analysis within days after an event. And this is supported by National Adaptation Strategy funding. In the big picture, the system that we're developing, it's based on two different sets of models. The first one is CMOS climate model simulations, as Lisa just described in her talk. We have a prototype in place for heat waves now. And there are other advantages of using coupled model simulations in that we can consider, other aspects of the coupled climate system, including, for example, the ocean. And then secondly, we're developing a system based on atmosphere model simulations with prescribed sea surface temperatures. We'll be able to run these at higher resolution, 100 kilometers and 25 kilometers resolution, to better simulate smaller scale events. And at the same time, of course, we're doing foundational research and model development to support robust statistical assessments of changes in extremes. Okay, so I'll describe now the rapid event attribution system for hot extremes in a bit more detail. Heat waves are the most deadly extreme event impacting Canada. The June 2021 heat wave that Lisa just described caused more than 600 fatalities, and so it's the most deadly natural disaster in Canada in recent history. And also heat waves are relatively well simulated in climate models, so those kinds of reasons mean that they're a natural place to start in terms of building a rapid event attribution system. So we've developed a prototype rapid event attribution system for heat waves based on the approach that Lisa just described. So she described the application to the 2021 heat wave, but in her paper from last year, there was also an attribution of the 2023 Alberta heat wave that happened in early May 2023. It uses the similar methodology, but it uses anomalies. It uses a moving 31-day window in order to look at anomalies from the seasonal cycle. And just to describe what the system does, we're using ERA 5. The system automatically downloads ERA 5. We're looking at 1-day extremes, 3-day extremes, and 7-day extremes, so TXX, TX3X, and TX7X, based on a 31-day running window. And the regions we're looking at are the Stone et al. Regions over Canada. Those are based on the provinces, but the larger provinces are divided into 2 regions, and some of the smaller provinces are grouped together. Okay, as I said, we're looking at anomalies relative to a 31-day running window, and we're comparing with CMIP6 simulations, CMIP6 historical simulations of 1850 to 1900 and of 2014 to 2033. So that's a 20-year period centered on the present. And the results are available within a week of a hot extreme occurring in one of these regions. And currently, like I said, it's a prototype system, but it's running automatically, and we're available to, the results are available to be shared in a reactive capacity in response to questions that we get following an extreme event. Work is underway to further improve the system, including looking at the effects of using other observational data sets, including ones developed within ECCC, which hopefully we might be able to get on a shorter timeline in order to be able to even reduce that 7-day lag after an extreme event occurs. We're also going to extend the system to attribute cold extremes and precipitation extremes by the spring of next year. Okay, the next couple of slides show some example output for an extreme, a hot extreme. In this case, these are focused on the May 2023 Alberta heatwave, and that heatwave coincided with the start of several large wildfires. As we heard about in the previous session, 2023 was an exceptional wildfire season in Canada, and some of those big wildfires in northern Alberta started during this period in May 2023 when we saw a big heat wave. So the figure on the left, and these are giving examples of the kinds of output that we'll be able to, or that we are able to provide rapidly following an extreme event. So the map on the left is the anomaly of daily maximum temperature for the 4th of May 2023. You can see that it was exceptionally warm across Alberta and also extending into parts of neighboring provinces as well. The figure on the right shows the average maximum temperature over Alberta. You can see, and the gray line is the 90th percentile of the climatology, and the red line is 2023. So we're using that as a kind of trigger criterion, exceeding that 90th percentile as a trigger criterion of when to carry out an analysis. Yeah, and as I already said, we're using anomalies relative to that 31-day moving window. Okay, so Lisa just described how we carry out this kind of event attribution analysis using CMIP6 output. So the figure on the left is another similar figure now for this is for 7-day maximum temperature, so TX7X over that 31-day window centered on early May for Alberta. Excuse me. So the green shows 1850 to 1900. The orangey brown shows 2013 to 2032, so the current period. And then the blue is the end of the century in SSP 245. Similar to what Lisa just described, the red there is the observations. In this case, this is the early May event in Alberta. And we can look at the probability of an event at least as strong as that which occurred in observations, both in the pre-industrial climate, and compare that with the probability in the present day climate. So if you like, we can look at the areas to the right of that line under the green curve and under the orange-brown curve. And then we can calculate a risk ratio from that, comparing those. And in terms of the products that we're planning to communicate from this system, we're planning to use kind of categorical statements based on the risk ratio, but not kind of giving a kind of undue level of precision, because of course there are uncertainties in the risk ratio. So in this case, our calculations indicate that the risk ratio the lower bound was greater than 2. So we would issue a statement that the event was much more likely because of human influence on the climate. And you can see the corresponding risk ratio definitions on the right. Okay, I think I'm on schedule here. So as I've described, in ECCC, we're developing a rapid event attribution system. We're planning to do it for a range of climate and weather extremes. Our initial focus is on hot extremes, although, as I already said, we are expanding that. And since heat waves are the most deadly extreme event affecting Canada, and also they're relatively well simulated in climate models, hot extremes was a natural place to start. And we've begun with a prototype rapid event attribution system for heat waves, based on the approach that Lisa published last year, and I should say as well that Lisa developed the code to do this automatically. So the event attribution results for heat waves are available within a week of an event for sharing in a reactive capacity as of now. We are planning to extend this CMIP6 based rapid event attribution system to cold extremes and precipitation extremes by the spring of next year. And as I described, we're also developing a system to carry out event attribution attribution analysis using atmospheric models, specifically CAN-AM and GEM. These models, we can run them at higher resolution, up to 25 kilometers resolution. So that will better allow us to better resolve smaller scale events, for example, precipitation events on smaller scales. I'll stop there. Thank you.
Great. Thank you so much, Nathan. There is one question for you so far. Have you considered looking at 20 CR products as well as CMIP for 1850 to 1900?
20 CR, so I think that is referring to the prescribed SST simulations that are coordinated internationally, the C20C plus. I think that's probably what it's referring to.
Sorry, Nathan. I think it's 20th century's climate reanalysis. I'm not sure, but
okay.
I think that's
okay. The NCEP reanalysis, the 20th century reanalysis. Okay, yeah. In terms of the observational products, we are looking at. In fact, yeah, Yongxiao Liang has been looking at using other observational data sets other than the ERA 5 reanalysis. There is. I mean, ERA 5, well, as Lisa showed, it is representing some of the extremes that occurred in BC in the 40s, but there is undoubtedly bigger observational uncertainty in the beginning of the record, and there are just observational uncertainties in these extremes over Canada, especially given the relatively sparse observing network. So yes, we are looking at other observational products. We're considering using the Canadian GDPR system and a reanalysis which is being developed based on that. We have Yongxiao Liang has looked at some other reanalyses, not NCEP 20CR yet, although that is one that we could consider. But yes, we are certainly looking at other observational products, and I think it is important to try and estimate the influence of observational uncertainty on our results.
Great, thank you. There's one more question we have time for. How will you communicate the climate influence on cold extremes?
Yeah, thanks for that question. So I'll just go back to this slide here. So you can see that, and actually, Megan was the one that developed these categories. So you can see that we have categories for both events that are more likely because of human influence on the climate, as well as events that are less likely because of human influence on the climate. So yeah, we have had some initial thought about that. Yeah, of course, we'll use a scale similar to this. I think the only question is whether we should reverse the color scale for cold extremes, because of course we expect warming to make cold extremes less likely. So maybe we should use warm colors for that. But yeah, we have had some initial discussion and thought about that. Thanks.
Great. Thank you very much, Nathan. With that, I think I will pass it back to Lisa to carry on with the other talk.
Thank you. Yeah, thank you so much, Nathan. So the next speaker is Yongxiao Liang, who's Nathan mentioned. Yongxiao is a research scientist at Environment and Climate Change Canada, and he'll be talking about probability estimation for long return period hot extremes using a large ensemble of model simulation. Yongxiao, you have 13 minutes. Thank you.
Okay, thanks. Hi everyone, my name is Yongxiao Liang. So I present a work titled Probability Estimation for Long Return Period Hot Extremes using a large ensemble of model simulations. And thanks to my co-authors, Megan Kashmir-Young, Xuebing Zhang, and also acknowledge very helpful discussion with Alex Cano, Elizaveta Malinina, and Nathan Gillett. So as an introduction, the motivation of this study, because heatwave have very dangerous impact on human health, infrastructure, and environment. So, however, the current knowledge, our current knowledge is still insufficient to precisely estimate this event probability, or saying the return period. So these estimations are very important to engineering practice for infrastructure design and management. And some recent study suggests that some existing method cannot well quantify the probability for the very rare events. So the objective of this study is to evaluate the limitations and reliability of the method to estimate the event probability, especially for those extreme events in very rare status, and also provide the suggestions for the optimal strategy to improve the estimation. The study area and event definitions, showing the left panel plot, we use the storm-defined regions. For the global land, we study each region separately and try to conclude the results over global land in general. So how we define the extremes, the reference events, as shown in the red panel here, provide you some example regions from North America. So we treat each study each region separately by making use of the large ensemble model, for example, KSM5, as shown in this plot. It's the TXX, the annual maximum temperature across the year from pre-industrial period till now, under the historical all-forcing experiment. The shading here shows you the range of 50 ensembles. So we define the extreme events under current climate, saying the last 20 years of the recurred, and across 50 ensemble we have, so which means we have 1,000 samples that can well define the reference events in 500 years return period, or we also define less extremes in 50 years, as showing the red and orange dashed line respectively. So with this benchmark reference event, we are defined using this 1,000 samples, so we can assess the event probability estimated by the traditional statistical method using this benchmark. So then we can have the confidence to see whether the method can well estimate those events for different regions. So we use the large ensemble, so which means we do not using observation here, because we use the assume the large ensemble model we use as the real world, and the event definition are from those large ensemble models. So so we can call it the perfect models analysis. So the fourth T method in the traditional method is make use of the observational time series itself to fit a distribution, then estimate the even probability by using this the time series of those observational samples. Um, for example, for BC Heatwave 2021, we can use the annual maxima temperature from observation record to fit the distribution, then estimate the even probability for the reference events. The climate is changes across the time from this time series. So the distribution is we call it no stationary. So the method we call it no stationary GV to fit these distributions. So there's a key assumption for this method, assuming that the local extremes, saying like TXX, as shown in this plot, driven by the global warming. So with these assumptions, making use of samples of we have from the time series, we can estimate the key parameters of the distributions. For example, using this regression relationship between TXX and the global mean warming as shown in the x-axis, based on these assumptions, so we can estimate the location parameter of the distributions by using the global mean warming quantities. So saying that if we have the T terms under the current climate, so for the global warmings, we can estimate the distributions for the factual world at the current climate, or even if we know the global warming at pre-industrial period, so we can get the distributions under the counterfactual climate. Based on these distributions, we can estimate the even probability for the reference events. So that's the method because no stationary GV. So because there's a strong assumption, so the local extremes is driven by the global warming. So there's maybe some additional local feedback independent of global warming against all this assumption. Also, we have the limit sample size to fit the distributions. So with these two concerns, we want to know if there's a limitations by using this method to estimate even probability. So how effective of this method to estimate the even probability, especially for the events in a very long return period for the rare event. So what we use here is using the individual realizations. So what we use here is we use the individual realizations of 50 KESM ensemble, and using these individual ensembles to estimate the even the probability. So ideally, so if this method is robust, we expect the estimations across different ensemble can get very consistent even the probability estimations. So in the next slide, I will indicate the return period range across 50 ensembles. So I showed the results in the left panel. Here provide you for region from North America, and the y-axis here is the return period. So the bar here is the range, uncertainty range across 50 ensemble to estimate even probability. So the dashed line here is the empirical estimation for the even probability. Um, um, so in blue is the estimation for 500 years in 50 years, and in blank is the estimation for 500 years even. So we can see that the estimations based on this method for the very rare events get very large uncertainty. So the uncertainty can more than 1,000, which is a quite large range. Even this method can capture the range, can capture the empirical estimations. So if we see the results globally in the red for the map, so the bubble here represents the magnitude of return period uncertainty across 50 ensemble. If the color in red, it shows the empirical return period can be captured by the uncertainty range. So for 500 years, even we can see that the range, the bubbles size are mostly greater than 1,000 to estimate the 500 years even. For 50 years, there's something reduced for the size of the bubble, but given that it is 50 years estimation, so the uncertainty is still quite large. So our key message here, so there's a limit, there's some limitation by using this method to estimate the even probability in a very long return period. Sorry. The second method is by making use of couple models. We can pull the samples from different couple models. For example, if we Heatwave, we can pull the samples on the current climate or the climate around the 2021 to get enough samples to fit distributions. And those samples from different models, we treat it as stationary because we do climate hostile or stationary across the time by pulling those samples, and so we can fit a stationary GV. So usually the method is based on the annual maxima, daily maxima temperature, the TXX. So here we want to know whether this the stationary GV fitted to annual maxima, daily maxima temperature can reliably estimate the hot extreme, essentially for the extreme in very long return period. So because we have considered that the very rare extremes may not draw from the same distributions as the TXX, the annual maximum temperature. So we want to apply like the longer blocking length to generate the samples to see the distribution to see whether it can be the fitting can be approved. So the method we use is a stationary G, but using all of ensemble together and investigate the different blocking lengths to see the fitting performance. So because the reference even defined by the same models, and we use the models samples the same as a reference even, so there's no model bias here, which is good for the assessment. So here show you the result from example regions, the events in empirical definition as doing the dash line, and the color in orange is the 50 years empirical estimation, and the color in red is 500 years empirical estimations. So it's based on the annual maxima for the estimation is shown in the blue, and based on the 10 years blocking length shown in the red. So we can see then for the 50 years for the estimation of 50 years sequence. So either the annual maxima or the 10 years, the longer blocking length can will estimate the probability. However, if for the very extreme events, like saying in 500 years, so using annual maxima cannot will capture the even probability. The bias could more than 1,000. By using longer blocking can will resolve these issues. So you see the results globally over global land. So by using annual maxima showing the first row and 10 years longer blocking length as showing the second. So this the shading here is the estimation for the return period to estimate the event in 500 years. And the third row here shows the improvement by using longer blocking. So we show the results for the different large ensemble models. So you can see that by using annual maxima, there are many regions get the return period estimation more than 1,000. There's the overestimated return period by using annual maxima. But using longer blocking can resolve its issue over global land, showing the improvement. So the size of this bubble here shows a magnitude of improvement. So over global land, we can see using longer blocking then can get the better estimate, the reduced bias compared with annual maxima blocking. Saying that both regions for different models can get the improvement more than 500 years. So please note that here is the estimation for the 500 years even. So the improvement can be more than 500 years. So it is a significant value. So conclusion, so we suggest that the traditional method may not good enough to estimate the reference event in very long return period. So for different methods, so we we assess them separately. Using observation time series itself, we suggest there's a quite big uncertainty. And for using the carbon model, so we suggest for very long return period events, we using longer block events will resolve the bias. Okay, I stop here. Thank you.
Thank you. So we don't have time, but if you can very briefly answer the question which popped up in the chat. I assume this is using max likelihood estimation of the parameters. Have you considered Bayesian parameter estimation? They're typically more robust in shorter time series, especially when it comes to biases in return periods. It would be interesting to compare the two sets of parameter estimates in each of your scenarios. If you can answer very briefly, that would be great.
Sorry, what's the question? Sorry, I'm not follow up just now. Maybe I can answer in the chat later.
Yeah, that would be great if you could answer in the chat, because we have to move along. So the next presenter is Matthew Pereira-Wilson, who will be talking about extreme temperature events in the Pacific Northwest. Matthew, you have 30 minutes.
Excellent. Thank you very much, Lisa. So today I'll be talking about the research that I've been doing in my first year of my PhD with the supervision of Dr. Nathan Gillett and Anna Monahan. Just to make sure you guys can hear me, that's fine. Yeah. The title of my presentation is Extreme Temperature Events and Atmospheric Blocking in the Pacific Northwest. And so to get us started with something that we've heard a lot about today already, this is the Pacific Northwest heat wave event of 2021, which was this extreme temperature event that occurred at the end of June, at the start of July of 2021, where some regions of British Columbia saw temperatures going up to 20 degrees above the seasonal average. And the town of Lytton, BC also set the Canadian maximum temperature record at something like 49.6 degrees Celsius. This event was also very significant for the communities in the area, with over 800 excess fatalities recorded in both the US and Canada during the event. And at the time, we thought this was an extremely unlikely, it's been like a black swan event, with early rapid attribution studies here by Philip et al. 2022, estimating something like 1 in a 1,000-year event for this type of heat wave. Some years have passed since this event, and we've learned a lot about the processes that went to making it possible. I highlight just two here. One was the extreme soil moisture anomaly already at the start of the blocking event that was to be set up over the region. Really allowed the temperature anomaly to evolve non-linearly with the geopotential height anomaly during the event. And something that I found extremely fascinating is that the air parcels that went on to form the blocking ridge over the Pacific Northwest, so the air parcels at some elevation from the surface, were themselves warmed up quite significantly via latent heat release during a precursor atmospheric river occurring in the Alaska Panhandle. So my work will mostly look at atmospheric blocking, but I think it's also interesting to take into account these other processes that are happening at the same time. And so since 2021, as Lisa mentioned, there's also been this 1941 heat wave that occurred. And so at the bottom plot here is showing the yearly maximum temperature from era 5 from 1940 to 2022. And we can really see these two heat waves towering over the temperature variability in the Pacific Northwest region. The thing I'll add here from the two plots that I'm showing of North America, so these black lines are the 500 hectopascal geopotential anomalies with respect to the 1940 to 2020 period. And we really see the same pattern set up during these two events. So there's a atmospheric blocking system over the Pacific Northwest and a secondary high over the Eastern Canada, which is quite interesting. And And so, like I mentioned, we're mostly interested in the atmospheric blocking and its correlation to heat waves in the Pacific Northwest. This is broadly a well understood correlation. So atmospheric blocking occurs when a high pressure system gets stuck over a particular region for multiple days, usually 5 and longer. And in this situation, the high pressure system basically suppresses the formation of clouds in the area, which really allows for solar radiation to warm up the surface during this time period. And the blocking comes from the fact that the high pressure system deflects the typical storm path over the region and so prevents rain and precipitation from cooling the area during this time. Though the correlation between atmospheric blocking and heat waves is very well established, how we identify atmospheric blocking in simulations and the data is actually not as standardized. So for our work, we're using this index by Ndoping et al. 2012, which uses the geopotential height gradients from a given pixel in the meridional direction. And then it requires a 15-degree longitude extent and a 5 consecutive day duration in order to be considered an atmospheric blocking event. So just some general housekeeping here. I will be using the ERA 5 analysis dataset from 1940 to 2022, as well as the KENI-SM2 large ensemble, which consists of 50 ensemble members from 1950 to 2100. The main variable of interest is the 2-meter daily maximum air temperature averaged over this red region, which basically includes the area affected during the Pacific Northwest 2021 heat wave. And as I also mentioned, for our atmospheric blocking index, we're using the daily averaged 500 hectopascal geopotential height. For a definition of hot day, I'm referring to any day in which this red region has a maximum temperature over the 90th percentile of maximum temperatures over a 31-year moving window. And I'll also briefly note that heat event or heat wave, in my, I guess, notation, is any consecutive number of hot days. And I'll try to be consistent with this. Okay, and so then coming to our first result, this top plot is showing the frequency of atmospheric blocking during the summer months from 1980 to 2009 in KENI-SM2. And we broadly see the main blocking regions at the end of the oceanic storm track, so in the in Alaska and primarily over Northern Europe. The middle plot is showing the frequency of blocking given a hot day in the Pacific Northwest region. So again, here within this red square. And we see that there's a slight shift downward of this blocking frequency. And this is best shown in the bottom plot here, the percentile score of blocking given hot day relative to the background signal. And so we see that there's a significant strengthening of increase in blocking frequency in these lower latitudes when there is a heat wave in the Pacific Northwest. But if I could just redirect you back to the middle plot here. So this is the frequency of blocking normalized by the frequency of hot days. And so we see that at most there is 20% of hot days that have a corresponding blocking anywhere in the world. Most of those are in Alaska. And so it jumps out at me that this isn't a very significant correlation, as in most Pacific Northwest heat waves have no associated blocking event, according to this metric. And so digging a little bit deeper into this, what I'm showing here in this plot on the y-axis is a measure of heat wave intensity. So this is the a heat wave's maximum temperature, subtract the threshold temperature to define a heat wave. And on the x-axis is the fraction of Pacific Northwest area that's identified as being blocked by our Davini 2012 definition. And broadly, we see that there's no real correlation between these two variables. And in fact, 80% of the data is at this x equals 0 line. And so what's going on here? Does this mean that there's no correlation between blocking and heat waves? No, we don't think so. We think this is primarily because of our choice of index and potentially related to the space and time constraints that we impose on it. Just to look a little bit more into this, so this plot is showing the stacked geopotential height anomaly. And so the top panel is showing the signal during the hottest day of all heat waves in the CANI-SM2 simulation. And then the two columns on the left and right-hand side are showing the stacked geopotential height anomaly, the days leading up to the event and the days after the event, after the hottest day of the event, I should say. And so we see that there is a development of this high pressure region over the Pacific Northwest, which peaks when the heat wave reaches its maximum temperature. And so there's definitely a relation between atmospheric blocking and heat waves that's just not being captured in our index. Just for consistency's sake, this is the same plot, but for ERA 5, where really the main difference here is that we maybe see more significant low pressure system develop in the Gulf of Alaska before the heat wave sets up over the Pacific Northwest relative to CANI-SM2, which is interesting. But yeah, it's still just early work. Finally, I will also mention that in CANI-SM2, with our definition of hot day and heat wave, we see that the average duration of heat waves is expected to increase from about 3 days from the 1980 to 2009 period to 3.5 days towards the end of the century from 2070 to 2099. Which is, of course, interesting because our hot day definition is relative to a moving percentile. So this really implies a changing in distribution, the shape of the distribution. And so this brings me to my conclusion slide. We find that the Davini 2012 blocking index appears to be a poor indicator of atmospheric blocking that causes heat waves in the Pacific Northwest. So we'll need to investigate why this is happening and what better blocking indices might be out there for this work. And we also see that in CANI-SM2, the average heat wave duration is expected to increase over the century. As for the next steps, I'm also really interested in this particle backtracking trajectory to account for the energy budget of the air parcels that end up contributing to heat waves in the Pacific Northwest. And that's something that I hope to include in my analysis in the future. Thank you very much.
Thank you so much, Matthew, and thank you so much for being on time. I don't see any. Yes, there is a question. Have you looked at Caesarian differences in relationship between blocking and hot days, defined as hot for that time of year?
No, I have not. So I've been mostly focusing on heat waves in the summer, but that's something that I could easily do in the future, but have not. Thank you.
Okay, great. Thanks so much. Thank you so much, Matthew. So while we wait in the next speaker to put on their presentation, I just want to remind you to submit the question through the Q&A box at the Event Mobi platform. And then there is a lag between what we see as the presenters and what you see as the viewers on the Event Mobi. So please don't wait until the end of the session to submit your questions. Okay, and the next speaker is Shauna Ndoping and Jamie Robson, who are students from University of British Columbia, and they will be talking about the role of near-solstice solar radiation on the Pacific Northwest heat wave of 2021. Shauna, you have 13 minutes. Thank you.
All right. Well, hello, everyone. My name is Shauna Ndoping, and this is my research partner, Janie Robson. Today, we will be giving a short presentation on the Pacific Northwest heat wave of 2021 and near-solstice solar radiation's role in the extremity of the event. We would like to first thank NSERC and UBC Workland for funding our undergraduate research. As we continue to head toward increasingly dire climate scenarios, we find it important to study extreme events for better understanding of how and why they occur and for better preparation in our changing climate. This was a prime motivation to conduct our research. You probably have some idea about the Pacific Northwest heat wave of 2021. Perhaps you recall the words heat dome, or maybe you were following the wildfire progression over the news. The Pacific Northwest heat wave, or PNW for short, was one of the most extreme heat waves on record. It broke national temperature records of 45 degrees in yellow grass and surrounding area of Saskatchewan by 4.6 degrees Celsius on June 29, 2021 in Lytton, BC. Temperature anomalies were between 16 and 20 degrees Celsius between June 25th and June 30th. The extreme heat caused glacial melting, which in turn caused severe flooding in Western Canada. It also drove the most severe wildfire season up to that point. For reference, the 20-year provincial annual area burn was 284,001 hectares, whereas the 2021 fire season in BC burned 869,270 hectares. The PNW heat wave was linked to an omega blocking ridge, which contributed to the persistence of the event, with diabatic heating and adiabatic subsidence allowing the region to warm significantly. Air that drove the event came from the Philippine Sea, with over 40% of the air originating from below 15 degrees north. The heat wave was also linked to a landfalling atmospheric river. Water vapor and sensible heat transported via an atmospheric river influenced the extreme temperatures seen at the surface. Upwind latent heat gave way for a hotter troposphere above the region, which increased near surface temperatures. Low soil moisture was another contributing factor, although there is still debate between studies as to how much it influenced the heat wave. Through running models with versus without low soil moisture, it was found that the low soil moisture deepened the boundary layer, allowing for air near the surface to access the hot air aloft. The heat wave occurred between roughly June 25th and July 1st, although these dates vary plus or minus a day depending on who is asked. With this in mind, one can ask what the effect would have been of a heat wave with different solar radiation conditions, such as the radiation conditions in August, a period of time farther from the summer solstice. With June receiving noticeably more solar radiation in comparison to August, how much did the solstice have to do with the extreme temperatures observed? To conduct our study, we used the weather research and forecasting model, with our region of interest being the heatwave domain in green. We would like to thank Tim Choi for running the models for this study. To simulate the 2021 PNW heatwave, the model was initialized using ERA 5 data and ran between June 24th and July 5th, 2021. At the boundaries, the conditions were forced with ERA 5. For our heat wave, we define it as the period from 12 p.m. UTC on June 26, 2021 to 12 p.m. UTC on June 30th, 2021. And we ran heat waves 60 days ahead of the defined period, 30 days ahead and 30 days behind, corresponding to August, July, and May solar radiation conditions, respectively, with all conditions except radiation being the same as the month of June. Across all experiments, we found that our results were not sensitive to different land surface models and radiation schemes. One of the most important things we needed to do before we could say anything about our model results was checking how the model performs. To do this, we asked, does the temperature evolution over the area follow our forcing data? Do temperatures follow observations? And do we actually see radiation differences at the surface between the two models? We could see that over the entire heatwave box, WRF follows our observationally based forcing data quite well. The highest temperature of the heatwave was recorded in Lytton, BC, so we plotted WRF temperatures, ERA 5 temperatures, and the station data, and we could see that they correspond. The temperature highs are consistent for the time that we're studying. We can also see that between our June and August simulations, there are noticeable differences in incoming solar radiation at the surface. Spatially, we can see that there's a difference of approximately 80 watts per meter squared between August and June over the heat wave region. Moving on to our results. By observing these maps, we see 2-meter temperature differences between the average June and the average August 2-meter temperatures over the heat wave region. The average June temperatures are considerably hotter, particularly in the lower mainland and the BC interior, as well as in most of Washington state. The highest temperature from these plots for June was 49.1 degrees Celsius, whereas for August, it was a slightly cooler 45.7 degrees Celsius. Here we plotted the June minus August differences. Given that our heat wave region is red, we can conclude once more that June had higher 2-meter temperatures. From these temperature plots, we see that decreased solar radiation in August yields lower 2-meter surface temperatures.
As a metric of heatwave severity, we've decided to use total land area of record exceedance. We use the ERA 5 maximum temperature reanalysis dataset from 1940 to 2020, and we take the heatwave records are found relative to June 26 to June 30th, 2021. Since there are non-negligible differences in between WRF and ERA over land, to quantify the records broken under August radiation, we take the difference in between a June WRF run and an August WRF run and correct our June ERA runs by that amount. Under June radiation, which are the actual temperature records, we see record exceedance of over 1,652,000 square kilometers. For reference, this is nearly twice the size of British Columbia. A large portion of these records are being broken by greater than 5 degrees and are concentrated over central BC, where the block spent the most time. Under August radiation, there are far fewer records being broken, and records are being broken by a smaller margin. The total area of record exceedance under August radiation is 275,000 square kilometers and is an 80% reduction from the June heat wave. Records are being broken by the largest margin over the mountains, although there are some records being broken over central BC. So any record exceedance is already significant, but one interesting aspect of the 2021 Pacific Northwest heat wave was the sheer margins of record exceedance. The national temperature record was broken by 4.6 degrees, and there were many areas in the Pacific Northwest where records were being broken by 5 degrees Celsius or even 6 degrees Celsius. Because of this, we've also decided to quantify the area of quote-unquote notable or extreme record exceedance, which we've decided to define as 3 degrees Celsius. Between the two radiation scenarios, there is a reduction of 98% in records being broken by greater than 3 degrees. So under August radiation, not only are records being broken over less area, they are also being broken by smaller margins. As Shauna mentioned, we also ran sensitivity runs where we changed the radiation to match May and July, which are minus 30 and plus 30 days from the 2021 heat wave respectively. These are the record exceedance plots for all of our WRF runs. And we can see that May and July have smaller record exceedances than the control June. We would expect that May and July would follow June more closely than August, since the radiation curve begins to drop off around August, which is what we can see in the plots. Under May radiation, we do in fact see higher record exceedance than July, despite them being equidistant from the beginning of the June 2021 heat wave. This is because as time moves forward, the May simulation is moving progressively towards the solstice, so we're getting progressively more and more radiation, whereas in July, we're moving away from the solstice and getting progressively less radiation over time. However, it should be noted that neither simulation is warmer than the June control, which does support the conclusion that decreasing the amount of radiation does in fact decrease the severity of a heat wave in both area and marginal metrics. We also ran sensitivity tests to test our conclusions with two different radiation schemes. These are record exceedance under August radiation using either CAM or RRTMG radiation. We use primarily RRTMG radiation in our main simulations since it models heat wave daily maximums more accurately, which was integral to our study. The differences between the impacts of these schemes is quite small, and they perform comparatively in terms of area of record exceedance. Under RRTMG radiation, the area of notable or extreme record exceedance is slightly higher, but that does make sense given that RRTMG is slightly warmer. However, compared to the June 2021 heat wave event, we can see that there is ample evidence to suggest that radiation is in fact a factor influencing the heat extremes seen during the event. This conclusion also holds when we change the land surface model. Our main simulations use the NOAA MP land surface model since it also models heatwave maximums more accurately, which was a key motivation as our work relates to heatwave maximums. Using NOAA MP, records are broken by larger margins and the size of record, however, the size of record exceedance is quite similar. The area of notable or extreme record exceedance does change by about 7,500 square kilometers, which is, there's about 60%, like a 60% change in between the two land surface models in terms of extreme record exceedance. So in summary, we ran simulations of the 2021 Pacific Northwest heat wave and changed the levels of radiation while keeping all other factors the same. We show that there is less solar radiation in August than June, and temperatures do in fact decrease as a result. These results are consistent over different sensitivity runs, and all runs show that decreasing radiation does decrease the severity of a heat wave. We show that while a heat wave under August radiation could still have broken records, these records would have likely been broken over smaller areas and by smaller margins. And because of this, we can decisively conclude that time of year and therefore solar radiation was in fact a factor driving the 2021 Pacific Northwest heat wave. Thank you all so much for your time, and we would be happy to answer a couple of questions.
Thank you so much, Shauna and Jamie, and thank you so much for being on time. So we have one question from the chat. Climatologically, average temperatures are higher in August than in June despite the lower solar radiation. Does this mean that a weather pattern adjusted for August, say maybe increased water vapor in atmospheric river and higher temperature aloft, it could be even hotter than June 2021?
Did you want me to take this question? Or?
Yeah, you can take it.
Oh, okay. So the question was, could it be hotter considering water vapor?
Yeah, for example, if the weather patterns will be adjusted for August, yeah. For example, yeah, more water vapor in atmospheric river or higher temperature aloft. So.
I mean, it could be a possibility based on our study. Since we had just looked at solar radiation, we can't actually speculate on an exact temperature of how a heat wave in August would look like, simply because we didn't actually use August, but more so the August solar radiation conditions. So our study didn't actually look at, let's say, the land ocean feedbacks in August, as we do know August is hotter than in June. So for that reason, our specific study can't exactly speculate on that, but it is certainly something to look into and see what a heat wave would look like at that period of time, given those conditions.
Thank you. And as a chair, I'll also make a suggestion if I can. So it would be actually very interesting to see the same simulations, but for 1941 heat wave. Because I think, if I'm not mistaken, 1941 happened somewhere more in July kind of time. So it would be interesting to see how much hotter could it have been, possibly. Yeah, if it would happen at the same time as the 1941 heat wave. Yeah.
Most definitely.
Yeah. So thank you so much for a great presentation. So the next speaker is Stephen Sobie from University of Victoria, and while Steven brings up his slides, I wanted to remind everyone that we also have a few posters in the poster session tomorrow. So feel free to check out the poster session, and with each poster there are associated a link for the Teams room or Zoom room. So yeah, go check those out. And Steven now will be presenting about a presentation entitled Comparing Indices of Heatwave Frequency and Intensity in the Pacific Northwest. Steven, the floor is yours.
All right, thanks very much, Lisa. So yeah, this will be an overview of some analysis comparing heatwave indices in this region, and the work that I'll show was done together with my colleague Charles. So to begin with, very generally, heat wave indices can be categorized into roughly two main groups, and we've seen some examples in this session so far. So one is calculated primarily using just temperatures alone, and the other is indices that combine temperatures with other variables, often to provide more useful information about hazards related to things like human health. And there are other methods based on things beyond surface variables. But in this analysis, we're focused on these temperature-only based indices, and specifically the fixed temperature and percentile indices. But for future work, we're also considering incorporating these other parameters. So one important heat wave index to mention here is the definition established by the BC Heat Alert Response System, or BC HARS. So this is a province-wide system recently developed by the BC Centre for Disease Control and the Ministry of Health. And it's one that issues heat alerts based off of temperature forecasts from ECCC. And so their heat wave index is one based off of fixed temperature thresholds for 6 regions defined throughout the province of BC, which you can see here. And given the increasing importance of BC HARS for users, we've incorporated information from this system, specifically these temperature thresholds, into the heat wave indices that we've used in this analysis. So this is the main heat wave definition that I'll focus on. So this is defining heat waves with a temperature percentile based method. And so this is just showing daily maximum and minimum temperatures for 1 year at just an example site. And so for each day of the year, we're calculating temperature percentiles using a 15-day moving window approach over the year. And then in addition, we impose a lower limit on those percentiles using the temperatures from BC HARS. And so you can see that with these horizontal lines. And then we apply a persistence criteria that both of these thresholds must be exceeded for some number of consecutive days. So in this example, that's set to 2 days. And then when this definition is applied, it yields 13 days that's being classified as heat waves during this example year. And so one of the questions we're asking with this definition is, how does the frequency and intensity of heat waves change when either the thresholds or the persistence criteria are changed? And I'll show some results for this. So for the analysis, we've used 3 different data sets. So the first is DayMet, which is gridded observations based off interpolated stations. The second is ERA5 reanalysis that we've adjusted using PRISM climatologies. And then the last is stations from Canada and the US. For the gridded data sets, we've chosen to use these 2 because they are regularly updated to present. They cover both sides of the border, and they're at fairly high resolution once we apply this adjustment. And so these figures at the bottom here are showing the average annual hottest temperatures between 1991 and 2020, with the difference here on the right between DayMet and the ERA5 and PRISM data. And so you can see there are these areas of difference between these 2 data sets, and as you'd expect, those will be reflected in the patterns of heat wave frequency between those data sets. And so these figures are just showing an illustration of some of those differences. So the top panels are showing the annual heat wave days using the BC HARS definition alone. And so the left panel shows those heat wave days from DayMet, and then the right from ERA5 and PRISM. And so in this area, there are 3 of these HARS regions, which are shown by these boundaries. And so within each one of these regions, the temperature thresholds are fixed the same everywhere. And one consequence of that is that you can see sometimes sharp boundaries between some of these regions. So like between Vancouver and Lytton here, where the frequency changes somewhat abruptly from one region to the next. And in other areas, the HARS thresholds turn out to be fairly stringent values, and it means that the heat waves either occur infrequently or not at all. For comparison, these bottom panels here show annual heat wave days using the percentile method I described, with a 95th percentile threshold and 2-day exceedance required. And here you can see that the heat waves occur over more of the domain without any boundaries. And there's also a smaller range between the lowest and highest frequencies, since the thresholds are now more flexible to the local temperatures across the domain. Having said that, even in locations where the temperature data sets are relatively similar, heat wave occurrence can still be sensitive to small differences. So this is an example for Lytton, BC in 2015. So the top panel here is showing daily maximum temperatures between April and October for the 3 data sets, and then the bottom shows the same for minimum temperatures. And in each plot, you can see these lines corresponding to the temperature thresholds for each of the data sets. And so here, these are based off the 95th percentiles. And again, for this example, we're using a 2-day persistence for heat wave definition. And so using that index applied to the 3 data sets, we find there's one 3-day heat wave in early June in the station data, 5 heat waves between 2 and 4 days in length in era 5, and then none at all in day met. And this is despite very similar daily maximum temperatures. And so the heat wave differences here are arising from the minimum temperatures, and in particular, there's a little bit greater day-to-day variability in the station and day met during the events that are occurring in era 5. And in those cases, the station and day met minimum temperatures are exceeding the thresholds on single days, but they're dropping back down in between by sometimes only 1 or 2 degrees, but that's enough to break that persistence criteria. And so no heat waves are declared in those 2 data sets in sort of late June and early July. And so when that kind of thing repeats itself over multiple years, it yields different heat wave frequencies between these different data sets. And so just for comparison, this is showing the same kind of figures, but for 2021 in Lytton. And so here you can see that record-breaking event at the end of June, and all 3 data sets record that as a heat wave, as you'd expect. Although interestingly, it lasts for 2 extra days in era 5 compared to day met or the station. And then there's also this other small 2-day heat wave in era 5 earlier. And so one of the questions that we're interested in is what happens to heat wave properties when those definitions change. And so these are figures showing the average heat wave days per year as the threshold percentiles change from the 75th to the 99th percentile. So in this case for Vancouver, Lytton, Abbotsford, and Penticton. And so in each of these, you can see values from the 3 data sets using either 2-day or 3-day persistence required. And you can see that at all 4 of these sites, when you move to a more stringent threshold, the heat wave frequency goes down, as you'd expect, but it does happen in slightly different ways. So for example, in Vancouver, the temperatures at those percentiles are already pretty close to the BC HARS values that we apply as lower bounds. So just reducing the percentiles just bottoms out very quickly and the frequency becomes essentially constant. Whereas at Lytton and Penticton, you see similar sort of mostly smooth decreases in frequency until you get to the higher percentiles. And at all 3 of these sites, there's closer agreement between the station and day met, which is interpolated stations, whereas the era 5 and prism data tends to show more frequent events. And so in some of these cases, it may be overestimating that frequency. At Abbotsford, there's a little bit different pattern where you can see that at the lower percentiles, the frequency is determined more by the days required for persistence rather than the data set. And there's also greater overlap between the data sets in this case. And so again, these have these regionally specific features. And so this map is just showing an aspect of those percentile differences over the entire region, in this case, just from the era 5 and prism data. And so this is showing the difference in heat wave frequency between using an 85th percentile versus a 95th percentile. And so using that less stringent threshold yields about 2.5 times more heat wave days over the region on average, but the distribution of where those changes occur is concentrated, in the warmest areas of the domain, especially in the valleys and the eastern part down into Washington. Now, one of the ways we've used to define or to characterize heat wave intensity is with heat wave degree days. And so this measures the annual cumulative temperature anomaly above the heat wave threshold. And so it's similar in concept to cooling degree days, for example. And so this again is showing the values by quantile from low to high for 2- and 3-day persistence. And you can see these patterns are very similar to the frequency results. One of the main differences here is just that in Vancouver, you have this slow decline in the intensity of events instead of being flat from about the 80th percentile. But for the other 3 sites, it looks at least pretty similar. One interesting result that does show up, though, is if you consider the relative differences between individual heat waves. So this is showing a time series of heat wave degree days for Abbotsford between 1980 and 2022 with values from the 3 data sets. And so the top panel is showing heat waves degree days using an 85th percentile, 90th percentile in the middle, and then a 95th percentile at the bottom. And if you look at the 85th percentile, in recent years, there were these 3 relatively intense heat waves in 2009, 2015, and of course, 2021. And these 3 events are about 25 to 40 degree days. When you move to the more stringent thresholds, the first 2 of those events decrease in their intensity, whereas the 2021 event stays more or less the same. And so this is because that 2021 event was short, but very severe, whereas the others were longer, but not as hot. And so the relative intensity of heat waves can change depending on the definition. And this happens in other parts of the regions as well. So this illustrates some of those differences over the region as a whole. And so this is showing the difference in heat wave degree days during 2021 compared to the next largest other heat wave in the record. So the top is showing results from DayMet using 85th and 95th percentiles. And the bottom is showing results from ERA5 and PRISM for 85th and 95th percentiles. And you can see in each panel there are differences. The differences over most of the region are positive, which indicates that the 2021 event was the most intense. But you can see there are these regions of blue colors where that was not the case. And so the example in DayMet, this area around Seattle shows 2021 was not the most intense event in the 85th percentile, but that difference shrinks when moving to that more stringent threshold. Whereas in Penticton and south along sort of the Okanagan, that was more anomalous in 2021 than the next largest event. But when you move to the 95th percentile, it's actually not as anomalous. And there's analogous results in the ERA5 and PRISM data with this interesting feature around Harrison Lake. And so this case, the 2015 event lasted several days longer, which yields a longer accumulation interval for the degree days and makes 2015 a more intense event. But when you move to the 95th percentile, that effect disappears, and actually the 2021 event is again the most intense over that same region. And so the effect of changing heat wave percentile thresholds can have a meaningful difference in the relative heat wave intensity. And those events or those effects aren't necessarily the same everywhere. The other important thing to consider is that when changing percentiles it decreases the frequency of heat waves at higher thresholds. And so that means there's a necessarily smaller sample size when calculating averages or for heat wave event indices. So typically with annually defined indices, there's on a 30-year interval, you have a sample size of 30 to calculate climatologies or averages, whereas with heat waves, depending on the definition, there be maybe more or fewer than that number. And so these panels are just showing the total number of heat waves between 1991 and 2020. And areas in orange or red have more than 30 events, whereas areas in sort of these yellow colors have fewer than 30. And so you can see there's differences between the data. Okay, almost done. There's differences between the data sets, but in general, moving to that more stringent 95th percentile results in far fewer areas that have at least 30 heat waves. And so again, that means moving to that smaller sample size when averaging or calculating event indices. And then, so that's another factor to consider when selecting a threshold. So yeah, so typically in the heat wave literature, the suggestion is to set those thresholds somewhere between the 85th and 95th percentiles, but which values are optimal sort of depends on what kinds of heat waves you are aiming to capture. And it really depends on which heat waves you're interested in examining, the more extreme or the more frequent ones. And so it's important to consider that the results from that choice are not necessarily the same everywhere as well. So yeah, so this just lists the key points, and I'm happy to answer any questions. Thanks.
Thank you so much, Stephen. We have a question from the chat. What is ERA5 PRISM data, and is it public?
Yeah, so it's just combining. It's a simple bias correction, basically, of ERA5 that other presenters have discussed and PRISM climatology. So PRISM is a high-resolution climatology developed for BC. It's based on a method from OSU that they've applied over the US. And all we've done is apply a monthly bias correction to ERA5 to increase the resolution so that we're not necessarily, or so that we're more comparable to the DayMet, which is already at 1 kilometer. So it's not a public data set, but it's could be relatively easy to calculate, and PRISM and ERA5 separately are publicly available.
Great, thank you so much. Yeah, it was a very interesting presentation, and particularly for me, a person who's working on heat waves as well, to listen to these different definitions and how it can all change. I don't see any more questions for now. Oh yeah, there is one more. how these heat wave indices relate to health impact. Is there a quantitative way to tell which one is best?
Yeah, it's a good question. So there's, I think what's often mentioned in the literature, there's not necessarily one standard. I think that as others have mentioned, and so with these, a choice you can make is to focus on maybe the most extreme or anomalous events, so using those more stringent thresholds. But obviously, if for events that are happening sort of early in the season, where people are not acclimatized to extreme heat, there you may want to consider lower thresholds because the sudden onset of very anomalous temperatures can have more health impacts than they might occur later in the season after people have been exposed to some higher temperatures and have been adjusted or have become adjusted. And then the other factors, yeah, some of those other indices I mentioned that incorporate things like humidity or radiation and others can give you potentially more specific information related to health impacts, for example. And so if you're really focused on those, some of those indices might be of more interest, like humidex or wet bulb globe temperature, for example.
Thank you. Yeah. We still have 4 minutes until the end of the session. I apologize if I was rushing the speakers because I miscalculated the time. But I want to let people know, so there were a few questions about 1941 heat wave, and Matthew nicely answered that in the chat. So please feel free to check it out. And yeah, otherwise, again, a reminder that we have a few posters tomorrow. And otherwise, if there are no more questions, we can finish a little bit early and have a health break. So we will reconvene at in 15, almost, well, more like 20 minutes for the third block of this session, which will be mostly about the dynamics and the influence of the dynamics of the extreme events and the influence of extreme events on the water cycle. So yeah, nous nous reverrons dans 15, presque 20 minutes. Et oui, pour le troisième bloc de cette session, il s'agit des dynamiques d'événements extrêmes et aussi leur influence sur le hydrosphère. So yeah, see you all in 15 minutes. Thank you.